Hi, thanks for joining me. First and foremost, I have to say a few apologies. This video and probably the next few videos will be slightly different to normal. I don't have access to my computer at the moment, something's wrong with it. So I'm filming all these from my phone and uploading them from my phone, which means I have to sort of film them all in one take. I've can't really put thumbnails on, there'll be no intro or outro, so apologies for that, but hopefully most of the maths will stay the same. And yeah, I'm going to try and stick to that once every other day upload schedule, which I have. Anyway, today I'm going to be evaluating this integral here. It's the integral from 0 to 1 of log x raised to the power of n dx, where n is just some non-negative integer. So it's either a positive integer or it's 0. Okay, and I guess one thing I should say is obviously log x is not really defined at x equals 0. So this sort of just means the limit is, if I call this thing here epsilon, this just means the limit is epsilon goes to 0 from the right hand side. Okay, but I'm just going to keep it at 0 for now, just for cleanness sake. Okay, if you want to have a go at evaluating this integral, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so what I firstly want to do is, before I have a look at this integral, I actually want to compute a limit. And I'm going to call this limit Ln. Okay, and this is going to equal the limit as x goes to 0 from the positive side of x times log raised to the n of x. Okay, and this is for n. This is for n being at least 0, but at one stage in this limit thing, I'm going to assume that n is at least 1. Okay, but I'll come back to that in a second. Firstly, as x goes to 0, x obviously goes to 0, and log x raised to the n either goes to infinity or minus infinity, depending on what n is, but in particular it goes to plus or minus infinity, so we've got a 0 times infinity sort of situation, and that of course is indeterminate. So we've got to use L'Hopital's rule, but firstly we've got to rewrite this thing here as the limit as x goes to 0 plus of log n x all divided by 1 over x. Okay, so now the top goes to plus minus infinity and the bottom goes to infinity, so we can actually use L'Hopital's rule. Okay, so let's use it. So let's differentiate the top. So we're going to get n times log n minus 1x times 1 over x, and that's divided by the derivative of 1 over x, which is minus 1 over x squared. Okay, so I've just taken the derivative of log nx using the chain rule, which is n times log x all raised to the n minus 1 times the derivative of log x, which is 1 over x, then divide by the derivative of 1 over x, which is minus 1 over x squared. Okay, I can multiply the top and bottom by x to get rid of this guy here and get rid of one of the x's in the denominator. So now I've got this thing here, but if I sort of factor out the minus 1, oh, I forgot to write limit here. If I factor out the minus 1 and n from the limit because they're constants, this guy here just equals minus n times the limit as x goes to 0 of log x to the n minus 1 divided by 1 over x. But that's essentially the same thing as this guy here, except with the n replaced with n minus 1. So this is just precisely L n minus 1. So this is in the case where n is at least 1. Okay, so I'm defining Ln for n at least 0, but to sort of use this argument here, I have to assume n is at least 1. Anyway, I can sort of use this inductively and actually end up with Ln is equal to minus 1 to the n times n factorial times L naught. Okay, so how have I got from here Ln equal minus n, Ln equals minus n times Ln minus 1? How have I got from there to there? Well, I've just essentially replaced Ln minus 1 here with minus n minus 1 times Ln minus 2. Then I replace the Ln minus 2 with minus n minus 2 times Ln minus 3, and so on. And then you sort of use it inductively to get this formula here. If that doesn't make any sense, then I claim that this formula here is true. And now we can check that it's true in the base case when n equals 1 by just looking at, well, from this thing here we have L1 is equal to minus 1 L naught. And if you plug in n equals 1 here, we get minus 1 to the 1, which is minus 1, times 1 factorial, which is 1, so minus 1 times L naught. So it works in the case n equals 1, and then you can prove the formula sort of using induction, using this guy here. Okay, so I won't go into too much detail, but this thing here holds. So Ln is equal to minus 1 to the n times n factorial times L naught. Now what is L naught? Well, if you just go back to how we defined Ln, L naught is just the limit as x goes to 0 plus of x times log to the 0 of x. That's just log x raised to the 0, and anything raised to the 0 is 1. So this is just the limit as x goes to 0 of x, and of course that is 0. So in fact, ln equals minus 1 to the n times n factorial times 0. So of course the 0 just annihilates everything. And this thing here equals 0. And that's in fact for all n bigger than or equal to 0. Okay, so ln is equal to 0 for all non-negative integers n. Okay, what I'm going to do is rub off this and keep this limit here. And then we're going to use that to evaluate this integral here. So if I just rub all this off. Yeah, apologies, I can't sort of cut frames. I've got to film this all in one go. Let me just write it up here. The limit as x goes to 0 from the positive side of x times log to the power of nx is equal to 0. And that's for all natural numbers n. And all non-negative integers n. Okay, now let's go back to our integral. And the way we're going to do that is by parts. So our u is going to be, in fact, the whole integrand. So log x all raised to the n. So that implies that du is equal to n times log n minus 1 of x times 1 over x dx. So that's just using the chain rule, differentiating this guy here. Then our dv is just going to be dx. And that, of course, means that v is just equal to x. So now just using our integration by parts, we get that in is equal to uv evaluated from 0 to 1. So uv is just this guy here times this guy here. So x log n x from 1 to 0 minus the integral of v du. So this thing here, so that's minus n times the integral from 0 to 1 of x times log n minus 1 of x times 1 over x dx, like so. First and foremost, this x and that 1 over x cancel. So I'm just left with the integral from 0 to 1 of log to the n minus 1 of x dx. But that is just precisely I n minus 1. Okay, so in is equal to this term here, minus n times in minus 1. Like so. Now we need to just evaluate this guy here. So when I plug in x equals 1, I get 1 times log log 1 all raised to the n. Now we're assuming here that n is at least 1, so I guess I should write that here for n at least 1, but that's kind of already given from the fact of this n minus 1 here. Okay, so n is at least 1, so when you plug in x equals 1 into this guy here, this guy's always going to vanish. And now when I take the limit as x goes to 0 from the positive side, this is just the limit as x goes to 0 of x times log n x, and surprise, surprise, we worked that out earlier, that's 0. So this thing here is just 0 minus 0, which is 0, of course. So in fact, we get that in is equal to minus n times in minus 1. Okay, and that's for n at least 1. But then we can use the same thing we did before, sort of using an inductive argument. This implies that in is equal to minus 1 to the n times n factorial times I naught. Okay, and again, if that going from this line to this line doesn't make that much sense, start off with this as your claim, then prove it by induction. So the base case n equals 1, it's quite trivial to check. When n is 1, you get I1 equals minus 1 to the 1 times 1 factorial times I naught, which is precisely what we have here. I1 equals minus 1 times I naught. Okay, and then you can prove sort of the inductive step using essentially this thing here is the crucial point. Anyway, that's what we have. Now I guess the last thing to do is just check what I naught is. What is I naught? Well, that's the case when n equals 0. So we've got log x raised to the 0, which is just 1. So we're just integrating 1 from 0 to 1. So of course that's just 1. So this thing here is 1. A lot of 1s. So in is equal to minus 1 to the n times n factorial. And that is our integral evaluated. I hope you have enjoyed this video. Again, apologies that I can't have an intro or outro or anything like that. But hopefully within a week or two, I'm not sure how long this is going to take, I can get back to normal looking videos. Anyway, thanks for watching. I'll catch you in the next one. Have a great day.